Hello, everybody. So today we're going to go through chapter 3 with calculations with chemical formulas and equations. Okay, so let's just do a little bit of vocabulary real quick, so we can proceed, and you will know what I am talking about. So, a molecular weight is defined as the weights of all atoms together in a molecule of a substance. So specifically, molecular weight is used for molecules. Formula weight is basically the exact same thing. It's just for all compounds, whether it is a molecule or not. If you get these two confused, I don't really mind. It's not a huge deal. So the way that formula weight or molecular weight is calculated is by taking into account the molecular mass or the molar mass of each atom in a compound. So for example, we have this CHCl3, which is chloroform. The molar mass of carbon is added to the molar mass of hydrogen, which is added to 3 times the molar mass of chlorine. These are all added together, and you get 119.4 AMU. And keep in mind that AMU and grams per mole are just about the same thing. It's on the same scale, and so we can consider them to be the same. And so when we're talking about molar mass, specifically we're talking about the mole. And so a mole is a quantity of a substance that contains as many molecules or formula units as the number of atoms in exactly 12 grams of carbon-12. And so that is true, but also what it is saying is that the mole is a quantity. So just like 1 dozen equals 12, 1 mole is equal to 6.02 times 10 to the 23rd. It's a very large number, much larger than the number 12, but it is as well just a number. That's really all it is. So you can have a dozen eggs, you could have a dozen cars, you could have a dozen hats. Just like you could have a mole of eggs, you could have a mole of cars, you could have a mole of hats. It would weigh quite a bit because this number is so large, but it's just a little under like 6 trillion. That's how you could imagine that. Okay. And so a molar mass is when you have that number of things. You have 6.022 times 10 to the 23rd of, let's say, an element. Let's choose the element hydrogen. If you have that many atoms of hydrogen, then you are going to have 1.01 grams, or really it's going to be 1.0078 grams. And so this is saying that 1 mole, this number of atoms of hydrogen, is going to weigh this much. And so we call this the molar mass. It's measured in grams per mole. Grams per mole. And so these are the numbers that show up on the periodic table. If you have hydrogen, let's say we have hydrogen, it's going to have a 1 in the corner, and it's going to say 1.0078 in the other corner, and we'll put a box around it. This is what it would look like on the periodic table. You would have the symbol, the atomic number, and then the molar mass, and saying that, so just to reiterate, this number, 6.022 times 10 to the 23, that many atoms weighs 1.0078 grams. That's the number that you would find on the periodic table. And so that number is going to be given in grams per mole, because that's how many grams there are if you have 1 mole of those hydrogen atoms. Okay? And so, if we use carbon-12 as another example, we have a molar mass of 12 grams per mole, because carbon-12, 1 mole of carbon-12 weighs exactly 12 grams. 1 mole of 12C weighs 12 grams. Okay. It's also very likely. It does not always work exactly like that. That's why it's based on carbon-12, but it is also very likely that if you were to say have uranium-238, then 1 mole of this, 1 mole of uranium-238, 1 mole of U-238 is going to weigh a number very, very close to 238 grams per mole. Very close to it. The reason for that we may get into, but it has to do with how these numbers are calculated, nuclear chemistry, and the fact that neutrons and protons are a little bit off from one another, just a little bit. Okay, and so if we wanted to determine the mass of a chlorine atom in grams, this is how we would do it. So we get this number directly from the periodic table, 35.5 or 35.45 grams per mole. And so if we are talking about trying to weigh this, then weigh the mass of 1 chlorine atom. This is how we would go about that. So 1 chlorine atom is our starting number, and this is eventually what the equation is going to look like, but we can also do it with this train track method. So 1 chlorine atom is our starting number, and so 1 Cl atom, and then we're going to use Avogadro's number. So Avogadro's number is 6.02 times 10 to the 23rd things in 1 mole, and so that thing could be atoms. So what we'll say is 6.02 times 10 to the 23rd chlorine atoms, Cl atoms, is equal to 1 mole. And 1 mole of chlorine atoms, we do know from the molar mass, the moles is on bottom here, and the moles is also on bottom here, that we are going to have 35.5 grams. And so this we will multiply by the top, divide by the bottom, multiply together, and we end up getting 35.5 grams. And we'll divide that by, everything else should cancel out. Atoms are canceled, moles are canceled, and so we just have 6.02 times 10 to the 23rd. That's just the number because we have already canceled out the units. And that is going to equal the answer that's given here, 5.90 times 10 to the negative 23rd grams. So if you are confused by it, go ahead and try it for yourself, and it should work out just the same. And so when you are converting from grams to moles of a substance, you should ask yourself 2 things. And I'm going to add one to this, but I'll explain these first. So from grams to moles of a substance, how much does a given number of moles of a substance weigh? This is going to be your molar mass. So this would be found directly on the periodic table. And then you should ask, well, this is basically the exact same thing, the formula unit. This is just for how many moles of a given formula unit does a given mass of a substance contain. This is basically the opposite. This is just saying how many moles. In a substance. So you might be given either of these pieces of information, molar mass or how many moles in a substance. And there's a couple other things that I want to add here. So if you are asked, that's going to be 3. If you are asked about number of atoms or number of molecules, you may need to use Avogadro's number. It's likely that if you are asked about the number of atoms, the number of molecules of a substance, or the number of formula units, let's put that there. You may need to know you may need to invoke Avogadro's number, and then you would be able to convert from one number to another. So if you're asked about the atoms or the molecules, you may need to use Avogadro's number. Okay, so let's give this one a shot. We will talk about it. So if we have the molar mass of zinc iodide, that is going to be ZnI2. We have 319 grams per mole. I don't really like these slides because you definitely should have some decimal points here, but they are not being used. But we do know that we have 3 significant figures, and so our answer should have 3 significant figures, right? We have 3 significant figures here, and those are the only numbers that we're going to be using. But keep in mind that the number of grams per mole, the units for here are usually going to have many more decimals. And so this is usually, the molar mass is not going to be your significant number limiter. It's not going to be the thing that limits your significant figures. Okay, and so this is our starting value, like we talked about in the dimensional analysis slides. We have a starting value, and that is going to be, usually the starting value is going to be 1 single unit. Sometimes it's not, but I'll try not to give you too many where that's not the case. But we have 0.0654 moles of ZnI2. And we need to cancel out moles of ZnI2, so we know that that unit's going to go on the bottom. And we are going to use the molar mass here. So we have moles and we have moles. And so we can use the molar mass here. If you don't know, just guess that you're going to use the molar mass. I would say that that's a safe bet. If you don't know where to go, try using grams per mole. If you're not sure, then try using grams per mole. And so we're going to use grams per mole here, and we have 1 mole, and then we have the molar mass up here, 319 grams of ZnI2. And so we have the grams of ZnI2, we have the molar mass of ZnI2, and we have, and that's all we need. And so we will just multiply the top together, divide by the bottom, which is just 1, so we'll just be multiplying the top, and we end up with this answer right here. So in this many moles of ZnI2, we have 20.9 grams. And so that's really because per mole, iodine is pretty heavy. It's pretty low on the periodic table, which means that it is going to be heavy. And so we can take a look at that real quick. And we have the periodic table here. Iodine is over here. It's 126.9 grams per mole, which means that per mole, you have quite a bit of mass. Per that many atoms of iodine, you have quite a bit of mass. Zinc is a lot lighter. We have 65.38, so that is a lot less mass. And so it does make sense that if you have 2 iodines on there, even though you don't have that much of a mole, you don't even have an entire mole there, you're still going to have 20 grams of zinc. 20 grams is like, I don't know, like 3 or 4 mice maybe. I don't know how to, I don't have a good example besides numbers of mice, but yeah, 20.9 grams, I guess it's 21. Okay, so The other thing that we are going to work with is percent composition. So this is like saying if I have carbon, let's say I have benzene. I like using this as an example. It's a pretty useful one. And I wanted to know how much carbon is present. I want to know how much carbon is present. Then this is how I would calculate that, and specifically by mass. You can also do this by mole. This is also a an option. You can calculate the number of moles of carbon and say that that is going to be you can calculate the mole percentage. And so since there are 6 moles to 6 moles here, that's a 1-to-1. You could say that that is going to be a 50%, 50 mole percent. But we don't care about that right now. What we're talking about is mass percentage. And so this is how we would find that. So we would take whatever we're looking for, that's going to be A, and we're going to divide it by the mass of that, we're going to divide by the mass of all of it. And we'll then multiply it by 100, and we'll use a percent sign because that can kind of be our units here. So multiplied by 100 times percent. And so if we wanted to determine the amount of carbon present in, I believe this is formaldehyde, then we would do this. So we know that carbon is 40% by mass. We know that hydrogen is going to be 6.73. Hydrogen is often very small. And oxygen is going to be 53.3. And so to determine the mass of carbons in this much of formaldehyde, 83.5 grams, this is how we would approach it. So 83.5 grams times 40%. So 40% is equal to 40 divided by 100, right? It's 40 out of 100, which is equal to 0.4. And so that's what we would put down here. And we say 0.4. And I will I'll move this a little so that this can be bigger right there. 83.45%. We're saying that this is our mass. We need to know how much carbon there is in it, and we know that it's 40% of the mass. And so we're saying 83.5 grams times 40% is going to be 33.4 grams carbon in 33.4 grams carbon in 83.5 grams of CH2O. Looks like this, by the way. C is an H, H. This is what they embalm bodies with sometimes. I think they use different chemicals now. So the first step in determining the formula of a substance is obtaining its percentage composition. So if you were looking to determine the formula of something new, then you need to know its percentage composition. There's many ways to do this in the real world. One of the ways to do this is called elemental analysis. And I know I've talked smack about elemental analysis before because it is a very, it's not a very scientific technique, honestly. It is, there's a lot of equipment that goes with it, and it can be very precise, but when you were talking about the actual technique to use it, it is questionable and easily manipulated, and not very important. But to understand chemistry, it absolutely is. So a sample with a known mass of the compound is burnt. So this is specifically an organic, or really it's just an organic compound. And it's burnt, which means it undergoes a combustion reaction. So just as a reminder, I'll put not Very good. I'll just put that there so that I have a reason to have that written there. But so just as a reminder, for a combustion reaction, we have, for a combustion reaction, there is this that must occur. So you have something with carbon, something with hydrogen. There could be oxygen present. And you would add O2. In the presence of O2, this is where this occurs. So in the presence of oxygen, and I want to put this little delta sign. This means a change in heat. And so this coincides with the change in temperature. Change in heat and change in temperature are different, but change in heat is what we're talking about here. And so the delta means that there is a change. Delta means change in chemistry, and so this is how we use it. But when you heat something up in the presence of oxygen, specifically some kind of carbohydrate, then you will always get out CO2 and H2O. This is always going to be what you get out the other side. You will always get out carbon dioxide and water. These are going to be your products. And so when something is burnt, you get out CO2 and H2O. And then the masses of CO2 and H2O are going to be related to the masses of carbon and hydrogen. And so that is because both of these compounds are going to contain carbon and hydrogen. And so this is where the stoichiometry comes into play, which we have not actually used that word yet in these slides, but this is going to be where it comes from. And from there, we can calculate the amount of carbon and the amount of hydrogen present. Okay, so for this example, we'll use a 4.24 milligram sample of acetic acid, which is completely burned. And I'll just draw acetic acid for you here. I think it's good for you guys to get a look at these structures, because then you will not be so unfamiliar with them once you have to draw them yourself. And so it's completely burned, giving 6.21 milligrams of carbon dioxide and 2.54 milligrams of water. And we want to determine the mass percentage of each element in acetic acid. And so, yes, we have gone over this, but I'm not 100% sure that I will give something like this on the test because I have not given much homework for it, I don't think. And so, yeah, but let's go over exactly how to do it. All right, so this is already given. And so what I'm going to do is I'm going to actually write this out again, and I'm just going to steal these numbers. So we have 6.21 times 10 to the negative 3 grams, and I'll steal that as well. And so let's calculate the grams of C. So so we want to know how much carbon was in the original sample. And just a reminder, let's write this out. So this is C2, we have 2 carbons, H4, we have 4 hydrogens, O2, okay. And so what we want to do is, we know that this is our starting material, but we also know that in our calculations, we're going to start with carbon dioxide and water because we need to back calculate. And I will move this away just over here so we can write the rest of the equation, but we know that it's going to interact with oxygen. And we also know that it is going to, in the presence of heat, make CO2 plus H2O. And so this is a good starting ground, but I'm gonna outline some steps. So first, one, if you don't know what's going on in a question, the first thing you want to do is write out an equation, and you want to balance it. Next, you want to find your starting material values. So SM stands for starting material. And those are going to be your reactants. And then you want to apply them. to dimensional analysis. And so this is likely the course that we're going to do. So let's go ahead and balance this equation just really quick. So we have 2 carbons on the left. We have 1 on the right. So let's put a 2 right there. Remember that when we're balancing equations, we want to do the oxygen last. That's going to be the last thing that we do. Hydrogen, we have 2 hydrogens right here, and we have 4 hydrogens on the left, 2 on the right, so we'll multiply that by 2. And so now we can balance the oxygens. And what's great about these combustion reactions is oxygen is all by itself. That being said, it is not always clear and cut and dry exactly what you need to write, what the stoichiometry is going to be. But let's just count up the oxygens for now. We might be able to, we might not have to do much work. So we have 2 oxygens times 2, so that's going to be 4 plus 2, that's a total of 6. Now, this isn't multiplied by anything, but it does have 2 oxygens in it. So if there's 6 oxygens on one side, 2 of them are going to come from this reaction, this C2H4O2, and the rest are going to come from this oxygen. And so we are going to put just a 4 right there. And so when you're balancing, remember that you do not want, you are going to want to, if you can divide all of the coefficients, so all of these numbers, by the same number, then you are going to have to do that. Something was incorrect in your stoichiometry when you were solving it, and so dividing all the numbers is going to be correct. And you must get a whole number at the end. And you'll notice, though, that there's a 1 right here. It's not necessarily shown because we don't show 1s typically when they're just by themselves. So, but you cannot divide that in any way besides itself to get a whole number, the number 1. So this is now balanced. Okay, so we've done that. Now, we need to determine the mass percentage of each element in the acetic acid. And so this is the general guideline that I want to use to do that. But keep in mind that we might write out an equation and not even use it, but we'll see. We'll see if we need to. And so let's start with carbon, because carbon only has 1 of the element we're looking for. We're going to start with carbon. And so we have 6.21 milligrams. Now I'm going to expand this so that we have it in grams, because we're going to be using the grams per mole. And so if we're in milligrams, we need to get out of grams. So there are 1,000 milligrams in 1 gram. And when you're doing dimensional analysis, remember the larger, I'm going to put this in a different color so that it does not bleed into that. But when you're doing dimensional analysis, larger unit goes with smaller number. So a gram is larger than a milligram, and so it's going to go with the larger with the smaller number, which is 1, and the vice versa. Small unit, big number. So 1,000 goes with the milligram, 1,000 is smaller. Let's go back to continuing this. So 1 gram, and then we will use the molar mass. So carbon dioxide, carbon is 12.01 grams. Oxygen, we will multiply 15.99 grams times 2 times. And then we will add those together, and we end up getting 44.0. I believe it's 44.0. What do they have over here? 44.0. Let's stick with that. So we'll cut off a sig fig there. It's fine. I don't really mind doing that right here because we only have 3 sig figs anyway, and so it's not going to matter too much. So 44.0. Also, this is CO2. Grams of CO2 in 1 mole of CO2. Now, this is the tricky part. So we want to know how much carbon is in that carbon dioxide. And so we have to separate this. We have carbon, and this is the way that I like to do it. So if you are unsure how to figure out exactly how much carbon you have in something, let's just pretend that we took this this molecule right here that we're trying to analyze, CO2, and we broke it apart. We did some kind of deconstruction reaction where we determined the number of moles in each one. So that would be 1C plus 2 O's. And so for every 1 mole of carbon, there's 1 mole of carbon dioxide, there's 1 mole of carbon and 2 moles of oxygen. And so when we're trying to determine the amount of carbon in carbon dioxide, this is what we'll do. We'll say that 1 mole of CO2 goes to 1 mole of C. And we are almost done. What we want to do next, I'm going to shrink this a little so that I have more space. We'll shrink just this part. So I have more space, and then, good God, and then we can continue. So 1 mole of C, and we want to know the number of grams that were originally in our reaction. So 1 mole of C, and we're going to use the molar mass of carbon, which is 12.01 grams. And so this is how we will approach it. We'll multiply the top together, divide by the bottom, and we will get our answer, which is going to be 1.69 times 10 to the negative 3 grams. 1.69 times 10 to the negative 3 grams. 1.69 times 10 to the negative 3 grams. And so you might notice here that they use this number instead. They have just done this first calculation for us, where they put 6.21 and they divided by 1,000 and made it equal to grams. So they just did that first. All right, and then the next part that we're going to do, you can see that there's a percentage right here, and they don't actually do the calculations for this, which is questionable, but they do, but I will show you how. So this is the amount of grams of carbon in, what is this, in acetic acid. So to determine the amount of the percentage of carbon, what you would do is you would say, well, this is how many grams of carbon are present. And if we look back, then we can see that to find the mass percentage, it's the mass of whatever you're looking at divided by the mass of the whole. And so we have the whole, which is 4.24. So that's going to be 4.24 times 10 to the negative 3 grams, and we'll divide that by, I'll put this down here a little bit, 4.24 times 10 to the negative 3, and we'll divide that by what we just found, and this is acetic acid, and 1.69 times 10 to the negative 3 grams of carbon divided by grams of acetic acid, we will end up getting, oh, my mistake. I always forget to do this, but you have to multiply this number by 100%. And then you will get 39.9 grams, percent carbon in acetic acid. Okay, and so rather than do the other one, because that one took a little bit of time, and I want to get on to the next thing, I would like you guys, if you haven't, to try this one at home based on what I've done here. So this one's a little bit trickier just because water is a little different, so I'll help you out a little bit. So when we're trying to determine the number of moles of hydrogen, so that would be this step right here, the moles of hydrogen in water, we're going to do the exact same thing. We're going to say H2O goes to H plus O. So within 1 mole of H2O, there are 2 moles of hydrogen, and there's 1 mole of oxygen. Okay, all right. I also got a tip that if you're having difficulty just describing what a mole is or how to use it, the best way to do it is to speak it out loud. Say it in a sentence. So I would say like this: within 1 mole of H2O, there are 2 moles of H. Something like that. And then see if it can make sense in your own brain. You are going to be the best teacher of yourself. Okay, and so we end up getting this for the answer for hydrogen. And then if we wanted to know the amount of oxygen though, well, these are percentages. So 100% of this compound is carbon, hydrogen, and oxygen, right? So that means that if we know the equals 100%, if we know the amount of carbon and we know the amount of hydrogen in percentage, then we can calculate the amount of oxygen. So we would say that the amount of oxygen is equal to 100 minus C plus H. And that's what you're about to see on the previous page, but I want to show something. So the reason that we can't use oxygen here and we can't use oxygen here is because we can't use these oxygens to do the exact same thing and calculate it. It's because there are 2 sources of oxygen on this side. There's an oxygen in this C2H4O2, and there is an oxygen in just oxygen, atomic or molecular oxygen over there. There's also 2 products that have oxygen in it, so it's going to be very difficult to tell exactly where that oxygen came from, so it is not done really. And so this is how you would find that, though, is you would be able to say that, well, for 100%, we need to just subtract the amount of carbon and hydrogen, and then we will be able to get the correct answers. Okay, so let's continue. This is exactly what I had just said before. We found the amount of oxygen by taking 100%, because we know that 100% of this is made of carbon, hydrogen, and oxygen. Took the amount of carbon and the amount of hydrogen and subtracted those from 100% in order to get the amount of oxygen. And then we have our answers here. Okay. All right, so this is the next step where we have the empirical formulas. So empirical formulas of a substance are written with the smallest integer subscript. So basically, you have these molecular formulas that describe kind of the shape, or they describe how things are connected within a compound. But the empirical formulas, which you're going to be getting out of elemental analysis data like we just saw. And so the empirical formula is going to be the lowest ratios of these things. So if this is H2O2, then we are only going to be we're going to be dividing both of these numbers by the same number, and we'll get H1O1 or just HO. And so we can then find the molecular. So if we wanted to use this for finding the molecular formula, we would want to know the percentage composition, which the empirical formula is going to help with. And we also want to know what the molecular weight is. Determining the empirical formula is going to be like converting the masses of elements to moles. And so we will have to do that. All right, I'm going to give you a second to just read this, give it a shot on your own. It's basically exactly what we did before. It's just a little bit different. Okay, so to determine the empirical formula of this compound, what we're going to do is we're going to take these different numbers and determine how much is present in the actual compound. So it's important to note that this compound only has nitrogen and only has oxygen in it. And what we want to do is we want to see how much those are in moles. So we could say that we have this mass to start with, but we want to convert each of the components that we have into moles. And so what we'll do is we'll set up another train track, and we'll just do basically what we did before. So 1.104 grams is going to be where you can use the molar mass. So note now that I'm putting the grams on the bottom, and that is because I need to cancel out these units. But we also have this line in between. We can treat that kind of like an equal sign. We can say that for every 15.99 grams of oxygen, we have 1 mole of oxygen. And so we can divide, or we can now find the number of moles by doing this. And we actually don't need this other section over here, so I'll just put an X through it. But that's going to be 1.104 grams divided by 15.99 grams. Oh, yes. Times moles. And we'll cancel out grams just like they're canceled out here. This is oxygen. We'll end up with just moles. And so I'm going to sneak peek over here to see what that number is. We have 0.06900. They use 16.00. 15.99 is more accurate, but 16.00 is acceptable as well. And we end up with 0.00690. Oh, was that too many zeros? Yes, it is. 0.6900. 6900 moles of oxygen. We'll do the exact same thing for nitrogen. We have 0.483. We'll divide that by grams of nitrogen, divide that by the nitrogen's molar mass, 14.01 grams, and then we'll say 1 mole, and that will give us the number of moles of nitrogen. And so the number of moles of nitrogen is 0.0345. So 0.0345 moles of nitrogen. And now what we want to do is we want to divide all numbers present by the lowest number. So that we get of moles. So moles, 0.0345. We'll divide that by 0.0345. We're going to get 1, because anything divided by itself is 1. So that's 1 mole of N. And then we have 0.0697 moles of O, and so we'll divide that by the smallest number of the two, which is 0.0345 moles of just moles. It's just a number, and we will get 2. That's going to be twice as much, right? 45 times 2 is 90, and 3 times 2 is 6. So that's going to be a multiple of 2, so 2 moles of O. Now this is our empirical formula. We have NO2. There's 2 moles of O, there's 1 mole of N. And that's exactly what we see on the next page, where we divide all numbers, the bigger mole number by the smaller one. And you also, it doesn't say this, but you also have to divide the smaller one by itself, and that's how you will get the number. So we have NO2, and the ratio of N to O is 1 to 2, so the empirical formula is NO2. And if we want to determine the molecular formula from an empirical formula, we need to multiply by some number the empirical formula weight in order to get the molecular weight. So we can also take the molecular weight. Well, it says it right there. It says it down there. Molecular weight. We will rearrange this by dividing both sides by empirical weight, and empirical formula weight, to get N, so we know what to multiply everything by. And so let's see that in action on the next page. So if we wanted to do, so go ahead and give this a shot actually, and then we can continue. So we have the percentages here, and we want to find moles of these percentages. And we also have 60 AMU. We want to find empirical formula. And then we want to find the molecular weight. And so I'll give you another hint before we start. Assume you have 100 grams of whatever you have. That way, 39.9% of 100 grams is 39.9 grams. 6.72% of 100 grams is 6.72. All right, give this a shot. I'm gonna take a bite of my pizza, and then and then I will show you how this is done. Okay. So we'll proceed. We're assuming that we have 100 grams of acetic acid. It's going to contain 39.9 grams and 6.72 grams of hydrogen and 53.4 grams of oxygen. And these are directly from the percentages. And so when we convert to moles, I'll give you an example of one. Let's just do this one because it's pretty straightforward, but hydrogen, we have 6.72 grams, and we will divide that by the molar mass of hydrogen, 1.0078 grams of H and 1 mole of H, and that will give us the number of moles. We'll end up with 6.67 moles of H. 6.67 moles of H. And I rounded for sig figs there as well. And so each of these this was exactly what was done with each of these. And then we end up getting the number of moles of H. And then we will divide each mole by the smallest one. So that's going to be this one. And keep in mind that 3.33 and 3.34 are so similar that we can consider them to be pretty much the same number. You might have to round if you want to get a completely round number like this, which is totally fine to do. But I would say don't round for something that is below 10% from what you're looking for. So what I mean by that is if you have, above 10%. If you have like a number that comes out to be 4.67, let's say, that is too low to be rounded up to 5. And so you would multiply by some number. And you might just have to test some out. But this one looks like it's going to be a multiple of 3, just because 66666 is what you get for 2/3. So that means that there is a 3 involved here probably. So multiply by some number to get a whole number. Whereas if you have something like 4.98, then you would round to 5.0. So if it's pretty close, if it's within 10%, I'd say 4.9 is iffy, but I think that it's acceptable. The numbers should work out to be pretty close to what you're looking for, but if it's something that's not quite that, then that is acceptable. Anyway, so we took each number, 3.3, we divided by 3.33, we divided this by 3.33, we divided this by 3.33, and we got 1, we got 2, and we got 1. And so the empirical formula for acetic acid is CH2O. Okay. And so if we know that the formula weight of CH2O is 30, because we can add 12.01 plus 1.01 times 2 plus 15.99 to get 30, then all we have to do to find what we need to multiply each of these numbers by is n. We have the molecular weight, we have the empirical formula weight, and so we will divide 60, which was given on the other page, divided by 30, which is going to give us 2. So that means that each of the subscripts will just multiply by 2, and we'll get the molecular formula from the empirical formula. Okay, so let's talk about stoichiometry. We've already been doing this quite a bit, but this is just extending it a little bit further. So when we're talking about stoichiometry, we need to talk about chemical equations. And so a chemical equation can be interpreted in terms of either the number of moles or ions or formula units, or the number of molecules or the number of moles. Either one's fine. So when I say something like NaCl plus H2O goes backwards back to HCl plus NaOH, this could be interpreted as molecules or formula units. I'm just going to say, I'm not going to say FU. I'm going to say formula units or moles. And so if this stoichiometry is when we are going to use the coefficients in these numbers in this equation in order to convert one thing to another. So if we, for example, these are all 1 to 1 to 1, but if we had H2SO4 plus NaOH, we would get H2O plus Na2SO4, and we would then have to multiply this by 2 in order to get that value, which means we multiply this by 2. And so now the ratio is different. We have a 1 to 2 and for some values and a 1 to 1 for others. And so we can interpret this as 1 molecule for every H2SO4 and 1 molecule for every Na2SO4 or something like that. Or moles. Moles are fine as well. Okay, so molar interpretation of the coefficients in a chemical reaction is going to help us calculate the moles of a product that we make. So however much we make, we can calculate that. And we can also convert those moles of products or reactants, so we can convert them from one to the other. And so these are the steps that we'll be using. We're going to start with whatever grams we have, use these grams to convert to moles using the molar mass. Mole A to mole B, so if we have like an A plus B goes to AB, then we will be able to use the mole ratio. This would be a 1 to 1 right there, and so A plus B going to AB would then convert from mole, you can then convert back to grams of whatever you were looking at. So moles of B to grams of B is going to give you the final answer of grams of B. Okay, and so let's give it a shot. We have Fe2O3. Take a second and try to name that for me, and then try to name this one. Okay, so that is going to be iron 3 oxide and carbon monoxide. And we have that converting to iron metal and carbon dioxide. And so we have this already balanced up here. But if we wanted to convert the amounts that we had, we would say, calculating the amount of iron oxide, iron 3 oxide required to produce 1 kilogram of iron, we'd start so this is not done correctly. So there is math here. but this is saying this is not the answer. This is calculating, this is if you were to start with 1 kilogram of iron oxide, how much iron would you make? So let's go ahead and do the iron, let's do the actual one that's produced, or that says here, that it says up here. So iron oxide, how much iron oxide is used to produce 1 kilogram of iron? So we have 1.00 times 10 to the third grams of iron. And we can start on either side. So this equation up here starts with iron oxide, because that's what it was, that's what it thought it was going to be solving for. But it's actually asking, if we start with 1 kilogram of iron, how much iron oxide did we use to get there? And so we will calculate that. And we're going to start on this side. So 1 kilogram of iron, and let's make that straight. 1 kilogram of iron. We will then use the molar mass of iron. So let's look that up real quick. And we have iron, which is right there, 55.845. So that's 55.845 grams in 1 mole of iron. But now we're going to use the conversion. So we're in moles of iron, so we can consider this moles of iron when we are considering how much iron oxide was used up. So we'll say that 2 Fe for every 1 Fe2O3. And so you could say moles, molecules, whatever you'd like, as long as we're using equivalent units. So 2 moles of iron to 1 mole of iron oxide, and then we'll use the molar mass of iron oxide, which is kindly given right here. And we need to get out of moles. So we're going to say 1 mole of Fe2O3 goes to 160 grams of 160 grams of Fe2O3. And so we're just converting into grams. And so I will let you do this math on your own, but you are going to get some grams. And remember that we are going to cancel out iron. We have grams of iron, moles of iron, moles of iron. We're going to cancel out moles of iron oxide and end up with just grams of iron oxide. And then whatever number you get out by doing this math should be the answer to the question. So you will know how much Fe2O3 you needed to use in order to get 1 kilogram of iron. And I will tell you right now, it's probably going to be a larger number than this. It's also probably going to be a larger number than this. Okay, so let's try a different one. And since the answer is there, I will help you out with this. So we need to know how much hydrochloric acid is going to react with 5 grams of manganese dioxide. So this is for the complete reaction. And so this is something that chemists do quite a bit, is determine how much they need, because they need to know how much you're going to put into a reaction. And so we'll start with MnO2. This is actually shown perfectly. So we have 5 grams. I'll make one of these. Again, we have 5.00 grams of MnO2. This is our starting value. Remember, our starting value usually has just 1 unit, so something like grams is just 1 unit, rather than something like density. That would be 2 units. So 5 grams. We'll use the molar mass of manganese 4 oxide, which is going to be 86.9 grams of MnO2 in order to be able to get into moles of MnO2. And now we can use the molar ratio because we have moles of MnO2. So 1 mole of MnO2 is going to convert, for every 1 mole of MnO2 used, you need 4 moles of HCl. So 4 moles of HCl. And we want to know the grams of HCl. If we were to stop right here, then we wouldn't quite be done, because we need to know what the grams of HCl is. And so for every 1 mole of HCl, we'll use the molar mass and we'll say that there are 36.5 grams of HCl. And so, just to be sure, grams of MnO2 we can cross out, grams of MnO2, moles of MnO2, moles of MnO2, moles of HCl, moles of HCl. The only thing we're going to be left with is grams of HCl. And so this is going to give us the answer that's below, 8.40 grams of HCl. And so this is how much HCl is required. The amount required to react with 5 grams of MnO2. There you go. The amount required to react with 5 grams of MnO2. And so this is where we can start to introduce the limiting reactant. So the limiting reactant is going to be a reactant that is completely consumed when a reaction goes to completion. And so if you think about it, we have 6.022 times 10 to the 23rd. And let's talk about just about hydrogen. If we're talking about this many atoms, remember this number is nearly 6 trillion trillion. It is 6 trillion trillion divided by 10. So it's just barely 6 trillion trillion. But this many atoms is only 1.0078 grams. And that's for hydrogen. So what I'm trying to say here is that this extremely large number of atoms is only going to be 1 gram. So when you're doing a reaction, you are never going to be able to get that reaction completely correct by just measuring it. You are never going to be able to measure out exactly this many atoms or a fraction of this many atoms compared to another substance. And not only would you have to do that once, but you'd have to do it twice. So like even in a reaction where you'd say HCl plus NaOH, getting this number and this number, going to H2O plus NaCl, getting this number and this number to be exactly the same is going to be nearly impossible. Nothing is impossible, but impossible to get numbers the same. And so what that means is that if it's nearly impossible to get these numbers the same, then one is always going to be more than the other. And so this reaction is not going to be able to complete if you have an excess of one compared to the other. So one will be in excess. One is going to be in excess, which means that the other one, the one that is not in excess, is going to be your limiting reagent, because the reaction can't go through. The limiting reactant, reagent, same thing really. The reaction can't go through if there is nothing else to react with. So if all of this is used up, then this reaction will not go through if there's no more of the limiting reactant. So when you're doing a limiting reactant problem, you want to balance the equation, you want to identify which one is the limiting reactant, and then you're going to do that by calculating the amount of product from the limiting reactant. And so this is my example for this. So if you have a recipe to make peanut butter jelly sandwiches, and you have 2 slices of bread, 3 scoops of peanut butter, and 3 scoops of jelly, this is what it calls for to make one peanut butter jelly sandwich. If you have 1 loaf of bread with 20 slices, 1 jar of peanut butter with 16 scoops, and a jar of jelly with 4 scoops, how many sandwiches could you make? And so let's write an equation to solve this. And so this is the answer down here, but let's go through it and do it. So let's say that this is our product. So bread is going to be BD plus peanut butter, which is going to be PN, plus JE, which is our jelly, is going to go to, you're going to go to the product, which is going to be BD to PN3 JE 3. And so the first step is to write out the reaction and then balance it. And so for bread, we know that we need 2 of them, and these are each by themselves, which is fantastic, but we need 2 breads for this reaction. We need 3 scoops of peanut butter, and we need 3 scoops of jelly. So this is going to be the stoichiometry of this reaction. It's 2 to 3 to 3 to make 1. And so we can start and find which one is going to be the limiting reactant. So first, we'll start with 1 of the elements of the sandwich, then we'll do another, and then we'll do another. And luckily, there's only one product here. Sometimes there's multiple. When there's multiple, you just pick one. And I think we're going to do that next, so I'll proceed. So, to BD, we'll start with the number. And so remember that this is going to be like breads per sandwich. So that would be our conversion factor, but we're going to start with 20. So 20 BD. We know that we need 2 BDs for every 1 peanut butter jelly sandwich. And so I'm going to abbreviate this PBJ because I don't want to write that out each time, but PBJ. For 2 breads for every 1 peanut butter jelly sandwich, and we're done. So from the 20 slices of bread you have, you can make, ooh, that's incorrect. You can make 10 sandwiches. 10 PBJs. Now, if you have peanut butter, then we got to do something a little different. Let's say that we are going to start with the amount of peanut butter we have. We have 16 PN. For every 3 PNs we use, we can make 1 PBJ. Oof. PBJ. And that comes straight from here. 3 peanut butters for every 1 PBJ. And so that's going to give us 16 divided by 3, which is a little bit over 5. Right, because 15 divided by 3 is going to be 5, so it's going to be 5 1/3 PBJ. And then we are going to do the exact same thing with the jelly. So that's going to be 4 JE is what we'll start with. And we'll use the stoichiometry from the equation. There's 3 JE. And there is 1 PBJ. And so 4/3 is what you're going to get out of this. You're going to get 4/3. You're going to get 1.33. And I'll even make this equivalent as well. So that's going to be 5.33 PBJ. And this is going to be 1.33 PBJ. And so 1.33 is going to be our answer. That's going to be our limiting reagent. Limiting. And that's because this one can make the least amount of PBJ. There's going to be excess bread because there's going to be more bread than you can make sandwiches. And there's going to be excess peanut butter because there's going to be more peanut butter than you can make for sandwiches. And so your limiting reagent is jelly. Okay, and so give this a shot, and I will continue in a second. Okay, so I've actually already solved this one, but I will explain it. So we have 5,280 breads. We're going to say that for the equation that we had on the previous slide, we have 2 breads for every 1 PBJ. That gives us 5,280 divided by 2, which gives us 2,640. We'll do the same thing and for the next value, which is going to give us 2,877.1, which I believe is going to be our peanut butter. So 2,807.1 or 208 points, my mistake, 208.7 peanut butter and jellies. And then we will also have, that's not right. This is the correct answer right here. And then we will also have 2007 PBJs from 6.022 jellies. And so again, our limiting reagent, if we go back to our slide that we've been working on, our jelly is going to give us about 2007. And so this is again going to be our limiting reagent. So you just find the value that gives the fewest moles. Find the value that's going to give the fewest moles from your starting material. Okay, so consider the reaction between zinc and hydrochloric acid. I will give you a second to do this, and then we will move on to the next part. Okay, so we have 0.3 moles of zinc and 0.52 moles of HCl. And so you can predict, oh goodness, how this is going to work. And we'll just write it out here. So we have 0.3 moles of zinc, and we don't have to go all the way to grams here. We can stop at moles. My cat is going crazy, and so I'm going to pick him up, and I'm going to keep going. We have 0.3 moles of zinc, and we can use the molar ratio. You want to get into molar ratio before you start to use, or you want to get into moles before you use the molar ratio. And so for every 1 zinc, we just need to choose one of these, but it's already given to us in the problem, 1 mole of HCl. So every 0.3 moles of zinc, we know that for every 1 zinc consumed, there's 1 mole of HCl that we get. So HCl we get. And so we can stop there because we only need to go to moles. So we'll get 0.30 moles of H2. And we'll do the same thing, 0.52 moles of HCl. Oh, my mistake. This should be H2, not HCl. H2, for every 1, nope. We'll use the molar ratio given here. So that's going to be 2 H2. And we will give H2, HCl. For every 2 HCl, we will give 1 H2. And so 0.52 divided by 2 is going to be 0.26 moles of H2 produced from HCl. So HCl is going to be our limiting reagent. Our limiting reagent because it makes fewer moles of H2 compared to the starting material. Okay, identify the limiting reactant. We already did that. Zinc is going to be in excess. And the smallest amount is going to be 0.26. So that's the maximum amount of H2 that you could produce from this reaction if you started with those amounts. Okay, I'll give you a second to do this, and then we will move on. Okay, so the grams of acetic acid that can be produced in a reaction between 20 grams of CH3CHO and 10 grams of O2 are going to be this right here. You have the remainder of the axis. This is also something that we need to determine right there. Oh, how'd that happen? And we have, and so we will begin. And so I'll just show you how this is done. We're going to start with the amount that we have in our hands. So that would be 20 grams and 10 grams. We will then use the molar masses right here. So that's going to be 44.1 grams. This is the molar mass of this right here, which is acetaldehyde, I believe. That's what it's called. Yeah, acetaldehyde. And then we use the reactant, the reaction ratio. So we'll go back and we'll see that for every acetaldehyde that you have, every two, you get two acetic acids at the other end. Or is that that's acetic acid? Yes. And so you'll use the ratio, the mole ratio, and you'll go from 2 to 2. And then you will get the number of moles of acetaldehyde you have at the other end. As well, you'll do the exact same thing with oxygen, where you have 32 grams of O2 for every 1 mole. It's going to take 1 mole for every 2 moles of acetic acid that are made. And so, since acetaldehyde only makes 0.454 moles of HC2H3O2, then you get 0.625, and you can get 0.625 moles from O2. Then this is our limiting reagent, our LR, because it makes fewer moles. So acetic acid is going to be our limiting reagent because it makes fewer moles. If you wanted to find the number of grams, well, this is how we would do that. So we also need to find out the amount of excess starting material. And so we would do it like this. So we know what the limiting reagent is. It's this right here. And so this is how many moles are going to be formed from this reaction. The limiting reagent is going to be, we will then work backwards in order to find how much of the excess there is. And so we've already said that there is, we know which one is going to be in excess. This is our limiting reactant. So CH3CHO is our limiting reactant. So the excess is going to be the other one. So we don't really care about this up here at all. So I'm going to skip down here. We have 0.454 moles, 454 moles. And then we're going to use the ratio. Remember, that is acetic acid to O2. That's our excess reagent. They can also write this like this, XS reagent. It's just a quicker way to write that, but it means the same thing. Excess reagent, that's going to be in then we can convert that to the number of grams by using the molar mass, and we end up getting the number of grams of oxygen that are used up in order to make this amount. So this is O2 used to make 0.454 moles. And then of, what is that, HC2H3O. And so if the initial amount was 10 grams, we just have to say this is the initial, and this is going to be how much was used, and this is going to be leftover. So you have your initial that you started with, your used amount, which is going to give you whatever is left over and did not react. And so this is how you would calculate the theoretical yield, is you would, it's basically you start with your limiting reagent, and then you will go to one product. see how much your limiting reagent will make of that one product. And that is going to be your theoretical yield. Okay. Your actual yield is what you get when you were to do this experiment in real life. So if you got an actual yield, this would be your measured amount, and that would be what you're going to use for your percentage yield. So your actual yield, let's say that you got 10 grams, and your theoretical yield was 100 grams. That would be 10 divided by 100, and then we'd multiply that by 100 again, and we would get 100%, we get 10%. So that would be your percent yield. The theoretical yield is what is calculated, but the actual yield is what you measure afterwards. And so this is another example. So like, let's say that you calculated that you would get 27.3 grams. If you calculated you get 27.3 grams of O2, but you only actually got 22.1 grams of O2, you would do this math. 22.1 divided by 27.3 is times 100%. That's going to be equal to 81.0%. Okay.